Section 7.2 Trigonometric Integrals. We have already gone through a lot of trigonometric functions and their integrals in Calculus 1 and the earlier part of Calculus 2. The purpose of this section is to deal with three important types of trigonometric integrals. Not everything, three types. Type 1 is sine and cosine type, like example 1, cosine to the third power. Example 2, sine to the fifth power times cosine squared. Sine and cosine. Let's go over to the next page. Sine squared, example 3. Sine to the fourth power, example 4. All those are sine and cosine types, and that's type 1. By the way, here's a summary version of that, but we're going to discuss all these in a moment. Right now, let me go over to type 2. And type 2 deals with tangent and secant, like this example 5 and example 6. Tangent and secant. Here's a summary version, and some further examples about tangent and secant follow here. Those are a little bit too advanced, especially example 8 here. And then type 3, we have sine and cosine again, but this time two different angles. Earlier we just had x, but this time, as in example 9 here, sine of 4x times cosine of 5x, so we have two different angles. In that case, we have to use these formulae, one of these formulae. And that's about it. So let's go over to this section using the Mathematica notebook I wrote, and here they are. Okay, by the way, in this Mathematica notebook I included some review version of it, some trig identities and example problems here. So if you need some review on trigonometric functions, here's a good section, and I'm going to leave this section 1 to the students. Let's move on to the first type, sine and cosine. Cosine to the nth power times sine to the nth power. How do we handle that? The key here is to recognize which is odd. That's the first criterion. If anyone is odd, then good. We're going to take y as something else, the other one, as a matter of fact. Here's a basic strategy. If we have cosine to the odd power, then we can decompose it into cosine to the even to the certain k power times extra cosine of x. Now, this even part can be rewritten as a function of sine, because cosine squared is 1 minus sine squared. So this can be completely rewritten as a function of sine, an expression of sine, and this extra cosine of x will be absorbed by the substitution computation. Y is sine of x, and if you do substitution, dy is cosine of x dx. That's the main strategy. If we have sine to the odd power, again the same thing applies here. Even power times extra sine, and that even part can be expressed as a cosine, 1 minus cosine squared to the certain k power, and this extra sine will be rewritten or will be absorbed by the substitution computation. Y is cosine of x, then dy is negative sine of x dx. If one of them is odd, we can use this kind of strategy, and let's go over to some example problem here. And here are a couple of good examples, A and B. Let's go with A, which is a little bit easier. Cosine to the fifth power times sine to the 0 power. So if you simply take y as sine of x, then everything will work out fine according to, well, this kind of strategy. Let's work it out. We'll simply take y as sine of x and dy is cosine of x dx. So cosine of x that comes out, that extra cosine of x that will come out, will be absorbed by dy. And let's work out this integrand. Cosine to the fifth power can be rewritten as cosine to the fourth power times cosine of x times dx. And that red part will be written as dy. Like that. And how do we deal with cosine to the fourth power? All you have to do is to recognize this Pythagorean identity. Cosine squared is 1 minus sine squared. So cosine to the fourth power, because that's even, we can write it as cosine squared to the certain power. And cosine squared is 1 minus sine squared. So after substituting everything, we have a y integral right here. 1 minus y squared, total quantity squared, and dy. And after that, it is just routine computation. All you have to do is just break up all these parentheses and apply the power rule one at a time. And finally, resubstitute y equals the sine of x back in, then we're going to get an answer like this. By the way, I'm going to introduce you a shortcut way to write the same thing, which is going to be quite effective in this kind of problem. Instead of substituting y, and just y part is going to be sine of x, so just leave everything but write it as d of sine of x rather than dy, where y is sine of x and then dy is cosine of x dx and so on. So we were able to save some time or some spaces simply recognizing this cosine of x dx, which I am highlighting in red, is the same as d of sine of x. And then because now this sine of x is just one entity, we can use a power rule for that, and then we have the final answer right away rather than having to use the third substitution after getting y expression. If you're uncomfortable with this shortcut, you don't really have to use it, but if you do, then that's actually very effective as a matter of fact. As usual, each extra step means one more chance, one more trap that you're gonna end up making some stupid mistake or something. So if you can find a legitimate shortcut and if you're comfortable with it, by all means use it. Let's do this one more time. Let's move on to problem B. This time you'll have to use substitution by y is cosine of x because we have fifth power right here. So sine has odd power, so we take y substitution as cosine. How do we end up? How do we do this? We have this kind of computation. Maybe I just showed it too quickly here, just the entire answer. Well, let's go through with this. Y is cosine of x because sine has odd power. So let's go over to substitution computation. dy is negative sine of x dx. And consequently, this sine to the fifth power can be rewritten as sine to the fourth power times extra sine. That extra sine will be absorbed by this dy computation. What did I do here? Actually, I use alternative way to write the same thing actually in this case. Dx is negative 1 of sine of x times dy, so I just substituted dx right away here. Oh well, that's legitimate method too. So this negative 1 over sine of x cancel out the sine of fifth power, so we have negative sine to the fourth power, and sine to the fourth power can be rewritten as 1 minus cosine squared. So what we have an expression of y. And then after that, just routine computation. Break up all the parentheses. First the complete square, and then this y to the 1/2 power, and then the negative sign. after all those power rule computation, substitutes cosine of x back in, and we're going to get the answer. We can use the shortcut methods too. Here, the sine of x dx will be replaced by d cosine of x, but derivative of cosine is negative sine of x, right? So it's negative of d cosine of x, so we have this extra negative sign outside. Everything is same from this point on, except that this is a little bit simpler, and here it is. Well, let's see. We went through a couple of examples where we have a odd power so that we can substitute y as something else. What if both of them are even? Well, one way to handle that is to use something called reduction formula, which I'm not going to talk about in this class. If you're interested in, go through some exercise problems at the back of our textbook, and there they are. But that's too much actually. So I'm going to stick to the kind of examples that you can do with these power reduction formulae. Cosine squared can be rewritten as 1 plus cosine of 2x over 2, and sine squared is 1 minus cosine of 2x over 2. So second power just became the first power, and as a trade-off, x inside became 2x. Let's go through an example that we have to utilize that, and here's one such example. Example C, sine squared times cosine squared. Both are even, so we do not have good way to substitute and then take care of this lone sine of x or lone cosine of x, as we had in this kind of examples here. These kind of things do not appear. So what do? We use the power reduction formulae like this. Sine squared x is 1 minus cosine of 2x over 2. Cosine squared of x is 1 plus cosine of 2x over 2. And after that, just routine computation. Denominator 2 times 2 becomes 4, so right over here we have that. And then just fold it over. Then we have 1 minus cosine squared of 2x. Okay, we have cosine squared again. So what do? We'll have to use the power reduction formula again. This cosine squared of 2x will become now 1 plus cosine of 4x over 2, because we have to double this angle inside. And now what? Everything is the first power, so we don't really need any further trig identity. Final preparation. This became, let me see, I think I made a mistake here. 1/4 times 1. Oh yeah, this is right. Excuse me. 1/4 times 1 is gonna generate 1/4, and then minus this 1/2 times 1/4. So I'm gonna get 1/8, and then minus minus plus. So I have cosine of 4x over 8, and 1/4 minus 1/8. After simplification, I'm gonna get 1/8. So that's why we had just this one. As a matter of fact, I just trusted you would be able to follow all this algebraic manipulation. After all, this is Calc 2. Okay. And then we have the final answer. Antiderivative of cosine is sine. And then we have to divide by this 4 inside, consequently generating 1 over 32. By the way, another method is to use the double angle formula for sine, and this generates a little bit simpler solution, as a matter of fact, but this is rather unorthodox. Usually the double angle formula for sine is not really a useful formula to apply for trigonometric integrals. The power reduction formula method that we have early on here is more standard method, which works all the time. Looks like we won't have time to go through this final problem D, so I'm going to leave this one to students, and then let's move on to the next topic in a moment.